Hello my dear students, welcome to IMS GATE Academy GATE Foundation course on digital circuit subject. In this particular session, we will discuss regarding the CMOS logic family. This topic is common for two branches, EC and instrumentation. Okay, so in the last class, we have discussed regarding the introduction of data converters. What are the basics that are required for data converters that we have covered in the last class? That topic is common for three branches, EC, electrical, instrumentation. Those who couldn't watch that particular session, so kindly watch that lecture in your free time. So in this particular session, we will discuss regarding the logic family basics. Okay, so all of you put the heading logic family. See, in the third chapter, hi, good evening, Gopal. In the third chapter, we have discussed regarding the various logic gates, right? So inside each and every logic gate, you will be having the electronic components, right? So whatever the electronic components, the set of electronic components that we require for implementing any logic gate, so together we will call it as logic family. Okay. Say for example, if you are using, hi, good evening Tirumala, good afternoon. So if you are using like diodes and transistors, okay, before that I will just discuss resistor and transistor. Suppose if you are having one electronic circuit, in that particular circuit, if you are using resistors and transistors, and with the help of that, if you are implementing a logic gate, then we will call that one as resistor transistor logic family. Resistor transistor logic. And if you are using diodes and transistors, then it is called as DTL, diode transistor logic. Similarly, if you are using transistors only, two stages, okay, then we will call it as TTL, transistor transistor logic. And then you are having ECL, emitter coupled logic. ECL, emitter coupled logic. Emitter coupled logic. Okay, so earlier days you are having various logic families like this. Okay, so whenever you want to implement any logic gate, okay, you can use various components with the help of resistors, transistors, or with the help of diodes and transistors, or with the help of transistors, or in the emitter coupled logic, etc. Okay, right. And then here in these logic families, say for example, whenever you are doing any experiment in your laboratory, then what you will do, you will take the breadboard. On the breadboard, you will connect various components, resistors, diodes, transistors, etc. And if you want to connect the components, electronic components, you will connect with the help of wires, right? So like that, in the similar way, here in all these logic families, physically you can connect these components with the help of wires. That means in all these logic families, whatever the electronic components that you are using, all those are like discrete components. Okay, just like you are doing the experiment on the breadboard. Okay, you are having various components like resistors, transistors, or diode, transistors, etc. Okay, and you are connecting the components with the help of wires. Okay, so that means you are having individually components. That's why we are calling it as discrete components. Okay, right. And here in all these logic families, okay, whatever the circuit diagram you're having, okay, the overall circuit diagram for the time being, I'm just making into two parts, okay, with respect to the supply voltage. Say for example, here we are using VCC. supply VCC, and from here we are taking the output, and here we are having the ground. See, supply line is there, ground line is there, reference voltage ground, and supply line is VCC, and between VCC and output we will use one resistor. Between VCC and output we will use one resistor, and between output and ground you will be having various components with respect to the logic. Okay, what are the logic family we have considered? Accordingly, you will be having the electronic components like diodes, transistors, etc. Okay, but in all these logic families, between VCC and output you will be having one resistor, that is a fixed resistor. Okay, and whatever may be the during the entire operation, see, according to the respect to AND gate, OR gate, etc. Okay, based upon the inputs you are giving, accordingly you will get output as 1 or 0. Okay, right, whatever may be the internally happening in the circuit, but throughout the operation, here you are having one resistor, and in this resistor always the current will flow. Because of that you will be having what? Power dissipation. That is called static power dissipation. Static power dissipation. Static power dissipation. Okay, so this is the drawback. Okay, irrespective of the operation or irrespective of the requirement, okay, throughout the operation, when you are using this particular circuit, throughout the operation, in this particular resistor always current will flow. Because of that you are getting power dissipation, and that power dissipation we will call it as static. Okay, later you are having MOS. The next technology is MOS. So here you are using MOS transistor, metal oxide semiconductor. So with respect to that you are having two logic families, NMOS logic family, and the other one is PMOS logic family. So here in this particular circuit you are using only one type of transistor, that is NMOS. Similarly here we are using one type of transistor, that is PMOS. Okay, now here we are using VCC, but when you are using MOS transistor, that time here we will use VDD. Okay, here VDD, supply line is VDD, and here we are having the ground. Okay, and from here we are taking the output. Now in the earlier circuit you are having resistor, right? So now that particular resistor we can implement with the help of MOS transistor only. Okay, with the help of MOS transistor only we can implement, but that particular transistor will be working in the depletion mode. MOS transistor works in the depletion mode. Okay, so here you will be having one resistor. So instead of directly placing the resistor, we are designing the resistor with the help of MOS only. Okay, we are keeping one MOS transistor here. That particular MOS transistor we are operating in the depletion mode, then that particular transistor will behave as resistor. Okay, now if you observe previous one and this one, here physically resistor is there, Now instead of resistor we have replaced resistor with one MOS transistor, but still since the MOS transistor we are operating in the depletion mode, obviously here physical component you can correlate like you are having physically resistor only, but instead of using real normal resistor you are using the MOS transistor, that's all. Okay, So that means whatever the drawback earlier we have mentioned here, static power dissipation, the same drawback will be there even in the MOS logic family. Same drawback will be there. Static power dissipation. Static power dissipation. But when compared to the previous one and this one, here in the previous case, we are having the components discrete. Whereas with the help of MOS logic, either NMOS transistors or PMOS transistors, we can fabricate on the chip in the integrated form, right? So on the single IC, integrated circuit, that means you are integrating the circuits on the same chip, right? So that means here we are using the components like integrated, right? In the previous case, it is a discrete components. On the breadboard, we are connecting the components, whereas here, whatever the electronic components we are using, all those electronic components we are fabricating or we are incorporating or integrating on the same chip, right? So here we are using integrated components. Integrated components are on the same chip, IC, integrated circuit. On the single chip, we are fabricating or integrating the transistors, right? So when compared to the earlier logic family, the advantage is we are able to incorporate all the electronic components on the same chip. That is the advantage, but still we are having the same drawback, that is static power dissipation. Now here we are using two types of transistors. In NMOS logic family, we will use only NMOS transistors, whereas in PMOS logic family, we will use only PMOS transistors. Now we will combinedly use, okay. Now in one particular logic family, if you are using both NMOS transistors and PMOS transistors, then together we will call that particular logic family as CMOS logic family. CMOS logic family. CMOS logic family. Here C stands for complementary. C stands for complementary. Complementary MOS. Here we will use both NMOS transistors and PMOS transistors. Okay. So here in this particular logic family, between VDD and output, we will use PMOS transistors. Between VDD, supply and output, we will use PMOS transistors. And between output and ground, we will use NMOS transistors. Okay, say for example, in one particular circuit, if you are using suppose 5 NMOS transistors, okay. So that means here we will use between VDD and output, we will use 5 PMOS transistors, okay. So together we are having 10 transistors. in that particular circuit, okay, right. Now if you observe, the functionality of these two transistors are complement to each other. Say for example, if NMOS transistor is on, the corresponding PMOS will be off, or if PMOS is on, the corresponding NMOS will be off. That means, say for example, here 5 PMOS transistors we are using, 5 NMOS we are using, together we are using 10 transistors, 10 MOS transistors we are using. But out of which based on the input combinations at any time, okay, at any time only half of the total number of transistors will be on. Suppose example, 3 NMOS transistors are on, the corresponding 3 PMOS transistors will be off. If 2 PMOS transistors are on, the corresponding 2 NMOS transistors will be off. That means initially if you are having total 10 transistors are there, throughout the operation only half of the total number of transistors, that is 5 transistors, are only on, right? So that is the, when compared to the previous case and this case, here between VDD and output we are having one MOS transistor that is working in the depletion mode. Because of that particular transistor is working as a resistor, okay. So in the resistor, if constantly current flows throughout the operation, because of that you are getting one power dissipation, that is called static power dissipation. Static power dissipation. Now in this case, we are operating, suppose 10 transistors are there, but throughout the operation, whatever may be the input combination you may apply, okay. So irrespective of that, out of total 10 transistors, okay, only 5 transistors will be on. Which 5 transistors has to be on, that will vary based on the input combination that you are applying at the input, right? So that means throughout the operation, no single transistor permanently will be on, okay, because based on the requirement you will be changing the inputs, right? The moment if you are changing the inputs, accordingly here the respective transistors, which transistor has to be on, which transistor has to be off, that automatically will be taken care of. So irrespective of that, okay, whatever may be, like whether PMOS transistors are on or NMOS are on, irrespective of that total number, if you focus regarding the total number, out of 10 transistors, if only 5 transistors are on, okay, for each and every input combination, that means now just compare, if all the 10 transistors are permanently on, okay, then because of that how much power dissipation you will get. With respect to that, if only half of the total number of transistors are on at any time, so that time how much power dissipation you are getting, if you compare both, obviously here you are getting less power dissipation, right? So that is the main advantage of CMOS logic. Low power dissipation. The power dissipation is low. Low power dissipation. Here, just like the previous one, the same advantage as it is there, integrated components. Here all the NMOS, PMOS transistors we are incorporating on the same chip. Okay, so in this way, if you observe, initially in the older days you are having all these logic families. Okay, so here we are having the discrete components, and then drawback is static power dissipation. Later, with the help of MOS transistor, we are able to incorporate or integrate on the same chip whatever the logic gates are there, or any circuit if you want to implement, with the help of MOS transistors you can fabricate or incorporate on the same chip. Okay, so that means one advantage is there, that is the integrated components. Okay, but still the power dissipation, the same drawback was there. Just to overcome this one, here we are using both transistors, NMOS and PMOS. Between output and ground we are placing NMOS transistors, whereas between VDD and output we are placing the PMOS transistor. See, say for example you are using the mobile, okay, say for example after the mobile battery got fully charged, okay, after that if you are using most of the applications in your mobile, suppose one mobile is giving like 8 hours battery lifetime, okay, and other mobile you consider after getting fully charged, if you are using most of the applications, okay, but suppose if it is giving only 4 hours battery lifetime, so which mobile you will purchase? Whether you will purchase the first mobile or second mobile. In the first mobile the battery lifetime is 8 hours, in the second mobile battery lifetime is 4 hours. Which one you will prefer? Obviously first one, right? Because here in the first case, even though you are using most of the features, but internally whatever the components that were there in the mobile phone, okay, so those are consuming less power. Because of that the battery life is increased, right? So that is the reason nowadays. Now if you observe, you might have noticed one observation here. In order to make it as resistor, we have used only one MOS transistor, okay, but here instead of one MOS transistor, suppose if there are 10 NMOS transistors, here also we require 10 PMOS transistors. So with respect to this single transistor, here the number of PMOS transistors that we are using is more, but nowadays on the same, whatever the technology was going on in the nanometer technology, etc., right? So in the less space, you are able to incorporate millions of transistors, right? So when you are able to incorporate more number of transistors, so here space issue was not at all there, right? So our main motto is, somehow or other, if we are able to minimize, or whatever the electronic components that we are using, if they consume less power, so that the battery life, or we can effectively utilize that particular circuit for longer time, right? So this is the main reason why nowadays we are, whatever the circuits are there, we are going to implement with the help of CMOS logic. This is the main reason, low power dissipation. So in your MTech, if you prefer the VLSI specialization, okay, so during that time, while you are studying the subjects, or while you are doing the mini projects, okay, you will mainly focus inside whatever the circuits you are having, either analog circuits or digital circuits. If you want to implement, you will use the CMOS logic family. That means set of NMOS and PMOS transistors you will use. And here the main requirement is low power dissipation. Okay, so mainly in the VLSI technology, VLSI specialization, when you are studying, see, whenever you are having any circuit or system, you will focus two parameters. One is the amount of power consumption that should be as minimum as possible. Okay, so that is the one parameter you will focus. And one more parameter, whatever the circuit or system you might be having, okay, after you are giving inputs to that particular circuit, how much time it is taking in order to produce the output. Okay, if it is taking more time, that means it is having more propagation delay. If it is taking less time, that means it is having less propagation delay. So if it takes less time, then because of that you are getting the output at faster, right? So that's why these two parameters, in general, whenever you do the MTech specializations, or when you are working in the industry of VLSI, based on the requirement application, you will focus on these two parameters. One is regarding the power consumption minimization, okay, that here you will deal about CMOS logic family. And in order to reduce the propagation delay, or in order to increase the speed of the particular circuit or system, okay, there will be a number of parameters will be there. So in detail you will learn in that particular course. Okay, so just I am giving the glimpse that why nowadays whatever the electronic circuits we are going to, whatever you are seeing in our day-to-day life, okay, with the help of CMOS logic only, why they are going to implement. This is the main reason. Okay, right. I hope all of you got the clarity up to now. If you are having any doubt, you can ask. Yes, I hope it is clear for everyone. Right. So regarding NMOS transistor, the logic symbol will be like this. So here you are having gate, this is drain, and this is source. Gate, drain, source. Okay. Similarly, you are having PMOS transistor. So here, just like it will be NMOS, but in addition to that, you are having bubble. That's all. Gate, drain, source. Okay. Gate, drain, source. Here, this is the NMOS. Here, this is the PMOS. You are having bubble. Okay. So just note down in what condition the NMOS transistor will be on, in what condition PMOS transistor will be on. So NMOS transistor will be on. NMOS transistor will be on if VGS is positive, if NMOS transistor will be on if VGS is positive. VGS means what? The voltage difference between gate and source. If if the voltage difference between gate and source is positive, that means if VGS is greater than 0, okay, if VGS is positive and VGS is greater than VT. VT is nothing but some threshold voltage or cut-in voltage. Just like diode, if you consider 0.7 volt or 0.6 volt, etc., you'll be having, right? So after applying, if you are applying the input voltage more than that cut-in voltage, then only the particular diode will be conducting, right? In a similar way, for the transistor also, if you are applying the input voltage, especially the difference between gate and source, if you are applying more than that threshold voltage, then only the particular transistor will be conducts, okay, right? Similarly, PMOS transistor will be on, PMOS transistor will be on if gate to source voltage, is negative, and modulus, if you take modulus of VGS is greater than modulus of VT. Okay, when you have taken modulus, then it will become positive, right? So that value is greater than that modulus of that cut-in voltage. Okay, right. So in general, when you are solving the questions regarding NMOS transistors, PMOS transistors in the analog circuit subject, so there in the questions or circuits, they will mention regarding that particular NMOS transistor, PMOS transistor, what is the threshold voltage. Okay, but regarding digital circuit subject, okay, so you can consider this VT as 0 volt. Okay, you can consider VT as 0 volt. So here we are considering like ideal case. Okay, right. So it is very simple. NMOS transistor will be on. If VGS is positive and VGS is greater than 0. Okay. Whereas PMOS transistor will be on if VGS is less than 0. Okay. If VGS is less than 0, and when you have taken modulus, it is greater than 0. Like that. Simple. So for the time being, let us implement the basic gates and then universal gates. Together, we'll discuss one by one. Okay, right. So all of you put the heading implementation of basic gates and universal gates using CMOS logic. Right. So first let us implement NOT gate. So here NOT gate output is Y, that is nothing but complement of input. See, just observe here you are having complement. Okay, under the complement you are having the variable A. Okay, so you are having single variable, so that means here we will use one NMOS transistor, one PMOS transistor. So this is the NMOS transistor. So this is your gate terminal, this is your drain terminal, and this is your source terminal. Gate, drain, source. Okay. Next, I am considering PMOS transistor. So for the PMOS transistor, this is your gate terminal, and this is your drain terminal, and this is your source terminal. Okay, right. So just observe here. Here in the CMOS logic, between output and ground, we are keeping NMOS transistors. Okay, and between VDD and output, we are keeping PMOS transistors. So here in this case, okay, So just observe, here I am connecting VDD, supply I am connecting, okay, and then here I am connecting the drains of both the transistors, and from that common point I am taking the output. Output V0. Okay, right. And here this particular source terminal I am connecting to the ground. Now just observe, between VDD and output, we are having PMOS transistor, and between output and ground we are keeping the NMOS transistor. Okay, and now here we are having gate terminals. Okay, so now in this particular example we will connect both the gate terminals tied together and we will give the same input. Okay, input Vn. See, when you are having the NOT gate, okay, for the NOT gate you will be having single input, and at the output you will get complement of the input. That is the reason here we have, for both the gate, okay, for both the gates of these two transistors we have connected the same input. Okay, right. So now let us understand whether this particular circuit is really behaving as NOT gate or not. See, here you can consider the truth table. Initially we will consider in terms of the voltages, and then I will represent the corresponding binary values. Okay, so here input and then output. Okay, so input voltage you can give either 0 volt or 5 volt. Okay, initially let us understand for 0 volt what is the output we are going to get, and then with respect to 5 volts. With respect to 5 volts or with respect to VDD, both are same. VDD 5 volt, both are same. Okay, VDD or 5 volt. Okay, right. So here I will write the corresponding NMOS transistor, what is the condition, whether it is on or off, and similarly the corresponding PMOS transistor, whether it is on or off. Yes. Now just observe, here first let us consider input voltage as 0. Okay, right. So here in this case VGS is nothing but VG minus Vs. VGS is nothing but VG minus Vs. Okay, so here in this case at gate terminal I have given input voltage as 0 volt. And what about source voltage? Source voltage was already connected to ground. Ground means 0 volt. 0 minus 0, that is 0 volt. 0 volt. Okay. So now just tell me, here we are getting VGS of NMOS transistor as 0 volt. Okay. But just observe this particular condition. Here VGS is 0. That 0 if you want you can consider. Okay. 0 we can consider as positive, right? Or if you want you can consider negative also, no problem. Plus 0 or minus 0 both are equal to 0 only. Okay, so that means this condition was satisfied. But what about this one? VGS is greater than 0. Is it satisfying? No, because VGS value we got 0, but that is not greater than 0. That is equal to 0, right? So that means in this case NMOS transistor is what? Off. NMOS transistor is off. Okay, I hope it is clear. Now let us try to understand what will be the condition for the PMOS transistor regarding VGS. Here in this case same, because both the gate terminals we have tied together and we are given the same input. So input voltage, gate voltage is 0. Now tell me what is the source voltage? What is the source voltage for PMOS transistor? Yes, now if you observe, here regarding the PMOS transistor, the source terminal was connected to VDD or 5 volt. Okay, so that means here 0 minus 5, which is nothing but minus 5, Okay, so that means you are getting VGS value as what? Negative. VGS value is negative. Just observe. Yes, we are getting VGS value as negative. And when you have taken modulus of that, when you have taken modulus of that, then you are getting 5, and 5 is greater than 0. Yes, it's true. It's true. So that means in this case, PMOS transistor is on. PMOS transistor is on. Simple logic. Okay, I hope it is clear for everyone. Now whatever the transistor here you're having, based upon here state, okay, so just the equivalent circuit you can visualize like switches, that's all, switches. See, in this case, NMOS transistor is what? Off. Off means you can consider this particular transistor like open switch, okay. So that means there is no connection between drain and source, okay, right. Or you can just simply remove this particular transistor, that's all. Just remove this particular transistor so that there won't be any connection between drain and source, okay, right. Now, regarding PMOS transistor, it was on. So that means when it is on, what will happen? The drain and source terminals will be connected together. Drain and source terminals will be connected together. So that means in this case, the output is connected to VDD. Output is connected to VDD or 5 volt, right? So in this case, we are getting output as 5 volt. 5 volt. See, we have given input as 0 volt, but we are getting output as 5 volt. We are getting output as 5 volt. Okay. Now let us consider the other case. The other case is what? Input voltage. That means at the gated terminals, we are applying 5 volt. Now in this case, all of you just quickly try to calculate VGS and just check the relation and tell me which transistor will be on in this particular condition. See, in this case, NMOS will be on and PMOS will be off. Okay, how it is, let us see. Here I have given 5 volt, and so in this case, VG is 5 and VS is same, 0 volts. So 5 minus 0 is 5. So in this case, VGS value is greater than, okay, VGS value is positive and it is greater than 0, right? So that means NMOS transistor is on. NMOS transistor is on. Okay. So regarding PMOS, gate voltage is 5 and source voltage also same, 5. 5 minus 5 is 0. Okay. So in this case, you are getting 0 volt. If you want that 0 volt, if you want to consider as negative, yes, you can consider. Okay. But is it greater than 0? No. That means the PMOS transistor is off. PMOS transistor is off. Okay. So in this case, the PMOS transistor is off. That means just remove this particular PMOS transistor from the circuit, whereas NMOS transistor was on. So that means here in this case, the drain and source terminals of NMOS transistors are shorted together. In this case, you are getting the path like this. Output is connecting to ground. Ground means 0 volt. Okay. So here, for understanding purpose, we have considered for each transistor what is the condition, whether it is on or whether it is off. After that, I have written the final output. Okay. So now just for simple understanding, what are the input voltage, output voltage we are having. Okay. Just for easy understanding, you can consider the variables. Input variable is A, output variable is Y. Okay. So whatever the tabular form here you are having, just consider this particular first 2 columns. Okay. And just I am writing the corresponding equivalent values in terms of the binary values. Now in this case, in general, we'll consider 0 volt as bit value 0, 0 volts as bit value 0, and 5 volt as bit value 1. Similarly, here you are getting 5 volt, that means bit value 1, 0 volt means 0. So if you are giving input as 0, you are getting output as 1, or if you are giving input as 1, you are getting output as 0. Okay. Complement of 0 is 1, complement of 1 is 0. So that means this particular circuit is behaving as NOT gate or inverter. NOT gate or inverter. I hope it is clear regarding the functionality of CMOS transistor. Simple logic. In CMOS transistor, okay, in CMOS logic family, okay, because we are placing the NMOS transistors between the output and ground, okay. So when this particular transistor is on, just observe, when you have given 5 volt, okay, when you have given 5 volt, here 0, 5 minus 0 is 5 and it is greater than 0, right? So when you are giving high voltage at the gate terminal when compared to the source terminal, that time only this NMOS transistor is on. But the moment NMOS transistor is on, the corresponding drain and source terminals are shorted. Because of that, output is connecting to where? Output is connecting to ground. So that means when you are giving high voltage, at the gate terminal when compared to source terminal, that time NMOS transistor is on. Because of that, at the output you are getting low. So that means when you are giving high as the input, you are getting low as the output, right? So because of that, in CMOS logic family, by default, from where you are taking the output, okay, in CMOS logic family, okay, from here we are taking the output, right? So between VDD and output we are keeping PMOS transistor, between output and ground we are keeping NMOS transistor. So from the intersection point of the PMOS and NMOS transistor, from there we are taking the output, and that particular output expression or function by default will be present in what form? In the complement version. That is the beauty of CMOS logic. Okay, so that means whenever you want to implement any Boolean function with the help of CMOS logic family, okay, so by default the output expression will be in the complement version. Okay, I hope it is clear for everyone. Why we are getting complement? Because here between output and ground we are using NMOS transistor. If you want to make NMOS transistor to be on, you have to give high at the input. Okay, if you are giving high at the input, because of that you are getting low at the output. These two are complement each other. That is the reason in the output expression by default you will get the complement version. Okay, so in the exam, okay, while you are solving the questions regarding the CMOS logic family, don't forget to put the complement. Okay, by default you are getting the complement version. I hope it is clear for everyone regarding the NOT gate with the help of CMOS logic family. So with this understanding, now let us implement 2-input NAND gate. Let us implement 2-input NAND gate. Two-input NAND gate. So here we will get y equal to AB bar. Okay, so just observe, previously we are having y equal to A bar. That means under the complement we are having only one input variable. Okay, so that is the reason we have considered one NMOS transistor. If you are considering one NMOS transistor, the corresponding PMOS transistor also you have to consider. Okay, right. Yeah, thank you Gopal, thank you. Okay, similarly, now if you observe under the complement you are having two variables A and B, right? So because of that we have to consider two NMOS transistors. The moment you are considering two NMOS transistors, obviously we have to consider two PMOS transistors. Okay, so for the time being, initially let us draw the circuit diagram between output and ground. Okay, once if you are able to draw the circuit diagram for output and ground in between that, okay, you are using NMOS transistors. Okay, with the help of that you can easily draw the PMOS transistors which are required between the VDD and output. Okay, right. So here in this case we require two NMOS transistors. Now tell me how we have to connect those two NMOS transistors. those two NMOS transistors. See, in the previous case, we require only one NMOS transistor, so there is no question how to connect. Simple. Between output and ground only we have to connect. But now we are having two input variables. Because of that, we have to connect two NMOS transistors. Now, whether we have to connect them in series or whether we have to connect them in parallel, all of you just think and tell me. See, here overall function you are having complement. Overall function you are having complement. So regarding that complement, I already mentioned, in the CMOS logic family, from the output terminal, by default you will get complement version. So you don't need to worry that one. Okay, right. So that is already there, no issue. Now tell me how A and B, among A and B, which operation we are performing. Okay, regarding complement I already discussed. Now just observe, you are having two variables A, B, among which we are performing what operation? Logical and. Whenever we are performing logical and, that means, see, regarding this particular concept we already covered in the second chapter. There I have started with the switches, like, right, switches, series connection, parallel connection, right? So that particular configuration in terms of the variables, how to represent, what kind of operator we can use, that we have already covered. Simple. Here we are having what? Logical and. Logical and means series configuration. Simple. Series connection. Logical and means series connection. Okay, if you are having logical OR, then that time we will use parallel. That's all. Here we require two NMOS transistors, and both the transistors we will connect them in series. That's all. Okay. So we require two NMOS transistors, and here you are having logical and, because of that we have connected series. Okay, right. Now we require the corresponding two PMOS transistors. So since we have connected NMOS transistors in series, the corresponding PMOS transistors we have to connect them in parallel. Here we are given the supply VDD, and then we are connecting these two. And from this intersection point we are taking the output, and here I am connecting the ground. Okay, right. So in the previous case we are having only one input variable. Okay, so that input variable I have given as a at the gate terminal of one NMOS transistor, and similarly at the gate terminal of the PMOS transistor, right? So in the same way, here, say for example, if you are giving A as the one of the input for one transistor at the gate terminal, same input you have to give here also at the gate terminal for one PMOS transistor. Okay, now I am giving one more input B for this particular transistor at the gate terminal. Similarly here for other transistor you can give the B input at the gate terminal. Okay, that's all. That means here if you are considering one NMOS transistor, the corresponding PMOS transistor will exist, right? So that means if you are giving A as the input for one NMOS transistor, similarly you should give as the input for one of the PMOS transistors here. Similarly here I have given B as the input, so that's why here also I have given. I hope it is clear for everyone up to this point. Okay, right. Now since you understood clearly regarding the NOT gate operation, so regarding NAND gate operation, directly we will take with the values, zeros and ones. Okay. So when you are having 2 bits or 2 inputs, you will get 4 combinations of zeros and ones. So just note down all the 4 combinations: 0 0, 0 1, 1 0, 1 1. These are the 4 combinations at the input side. Now let us analyze what kind of output this particular circuit is producing for each and every combination. Okay, right. So now just observe in the initial case. In the initial case, both are zeros. Okay, if both the inputs are zeros, just for easy understanding, you can observe here. When we have given input as 0, that time bit value is 0. 0 volt means bit value is 0. That time PMOS transistor was on. PMOS transistor was on. Okay, right. So in this case, both the inputs are zeros. Both the inputs are zeros. That means both the PMOS transistors are on. Right. Both PMOS transistors are on. Both PMOS are on. Okay. So in this case, both PMOS transistors are on. On means the respective source and drain terminals will be on or shorted. See, here source and drain are shorted, here also source and drain are shorted, and both are like parallel. Okay. So here you are connecting, okay, in this case output is connected to where? VDD. Output is connected to VDD. Yes or no? See, simple logic. Here on means simply these two terminals are shorted. That means you are having physical connection or wire like that. Okay. Here also you are having. That means output is connecting to VDD only. Yes or no? So output is connected to VDD. So that means you are getting 1. You are getting 1. Okay. So in this case, suppose if you consider here A value 0. If A value is 0, that means here left hand side PMOS transistor is on, but right hand side PMOS transistor is off. Okay. Since this transistor is on, anyway output is connected to VDD. Right. Okay. And similarly here B is 0. That means in this case this transistor is on, whereas this transistor is off, but still output is connected to VDD. So in these two cases, only one PMOS is on. Only one PMOS is on. Okay. In this input combination, this transistor is on. In this input combination, this transistor is on. Okay. Right. Now just observe last combination. Last combination. Both the inputs are 1. Okay. Before that, just observe. When we have given 5 volt as the input, that means bit value 1. That time NMOS transistor is on. NMOS is on. So if NMOS is on, we are getting output as 0 volt. That means bit value 0. Bit value 0. Right. So here we have given both A and B values are equal to 1. Okay. So for easy understanding, you start with B. Okay. B value 1. Okay. So that means this particular NMOS transistor is on. So in this case, the drain and source terminals of this NMOS transistor is on. So that means here at this particular terminal, the node voltage or at this particular point, voltage is nothing but ground only. Ground only. Now at the A input, we have given bit value 1. So that means this particular transistor is also on. Right. So these 2 points are shorted. These 2 points earlier shorted. Now these 2 points are shorted. So that means output is finally connected to ground. Output is finally connected to ground. So in this case, both NMOS transistors are on. In this case, both NMOS transistors are on. Now just observe this particular truth table, whether this truth table is related to NAND gate or not. Just observe, if you are considering AND gate, when all the inputs are equal to 1, that time you will get output as 1, for remaining combination you will get 0. Okay. Now just observe, here for when all the inputs are 1, that time you are getting output as 0, for remaining all the combination you are getting output as 1. Yes, this is the complement of AND gate, that is nothing but NAND gate, right? Complement of AND gate is nothing but NAND gate. Okay. Yes, it is very simple. It is very simple. You can correlate from the expression to the circuit, or you can easily understand from the circuit to the expression like that. Okay. See, in the gate exam, sometimes they will give the circuit diagram and they will ask what is the final expression you are going to get, or sometimes they will give the Boolean function or expression, okay, or for any logic gate, they will ask what is the minimum number of NMOS and PMOS transistor pairs required. Okay, see here we are using, suppose if you are using two NMOS transistors, obviously we require two PMOS transistors. Okay, together we will call it as pair, NMOS PMOS pair, here NMOS PMOS pair, like that. Here in this particular circuit diagram we require two NMOS PMOS transistor pairs, right? So these two variety of questions in general you will get from this particular chapter. Okay, right. So it is very simple. If you are having the Boolean function like this, here by default you are having, okay, in the given function itself you are having the complement, right? So regarding the complement there is no issue at all. Okay, so okay, in the CMOS logic directly you will get the complement. Now under the complement you are having two input variables. That means you require two NMOS transistors. Okay, two NMOS transistors. Now among those two variables you are performing logic line. Because of that we will connect those two transistors in series. The moment if you are connecting NMOS in series, the corresponding PMOS you will connect in parallel, like that. Okay, or otherwise, suppose you are having this particular circuit diagram. Now if you are supposed to write the output expression, okay, how you can write? It is very simple. Now just by looking at the circuit diagram, between output and ground you are having NMOS transistors, between supply and output you are having PMOS transistors. Because of that output expression by default you will get complement version, right? So don't forget to put the complement. In the CMOS logic by default you will get output expression in the complement version. That is the reason I am stressing this particular point multiple times, so that you people will never forget to put the complement while you are solving any question related to the CMOS logic, okay, while you are writing the output expression. Okay, right. Now just observe, just with the help of NMOS logic you can write the output expression, that's all. Here between output and ground you are having two NMOS transistors, and these two transistors are connected in series. Series connection means logical AND. Here you are having two input variables A and B, like that, that's all, AB bar. In this way, if you are having circuit diagram you can write the expression, or if you are having the expression you can draw the circuit diagram, okay, and then you can count how many NMOS PMOS transistors required. Okay, but for easy understanding, just by observing the expression also directly you can say, because here you are having two variables, that means you require two NMOS transistors. Okay, we require two NMOS transistors and we require two PMOS transistors. So together we will call it as two NMOS and PMOS transistor pairs. Two NMOS and PMOS transistor pairs. Okay, we require two NMOS and PMOS transistor pairs for implementing a two input NAND gate. Okay, so now we have implemented two input NAND gate. Now tell me how we can implement two input AND gate. How we can implement two input AND gate. Next one is two input AND gate. Two input AND gate. See, two input AND gate means output expression you will get logical AND among two input variables A and B. But what I have told, if you want to implement AND gate with the help of CMOS logic family or any logic gate, if you want to implement with the help of CMOS logic family, what is the first? By default, the output expression you are going to get in the complement version, right? So what you can do, whatever, here you don't have any complement, right? So whatever the expression you are having, just perform 2 times complement. Just perform 2 times complement. Whenever you are performing 2 times complement, you will get the same function, just like x bar whole bar is nothing but x only, right? So now if you carefully observe, here we are having AB bar. Okay, so regarding that, just now we have discussed This is the 2-input NAND gate using CMOS logic. Okay, so first I will consider that one. Whatever the circuit diagram we are having, okay, for the time being, instead of drawing the circuit diagram, I am just representing the block. So I am considering 2-input NAND gate. In CMOS logic, just now we have implemented 2-input NAND gate. So we will give AB are the inputs, output you will get AB bar. Now tell me what we have to do. Up to here we got AB bar we got. After that you are having one more complement. Okay, so regarding that we already discussed, this is the NOT gate or inverter, right? So that means whatever the output here we got, this output, if you are giving as the input here, then you will get the final output as AND gate, right? That's all. So here we are using the CMOS NOT gate or inverter. Okay, so at the output you will get whatever the input you are having, that particular input will get complement. So here you are having 2 times complement, that means you will get normal function, that is AB, right? So here for implementing 2-input NAND gate, we have used 2 NMOS PMOS transistor pairs, and for CMOS inverter we have used 1 NMOS PMOS transistor pair, right? So together we require 3 NMOS PMOS transistor pairs. 3 NMOS PMOS transistor pairs. We require 3 NMOS PMOS transistor pairs. Okay, so this is about AND gate. See, in the logic gates when we have studied, we have discussed initially AND gate, OR gate, NOT gate. Those 3 are the basic gates. And then we have discussed the universal gates like NAND gate, NOR gate, and then special gates like XOR gate, XNOR gate. But in this particular session, regarding this particular chapter, instead of discussing the basic gates, okay, that means AND gate, OR gate, NOT gate, in that flow, instead of discussing in that flow, I have directly considered the NOT gate first. The reason is, in the CMOS logic, by default you are getting the output function in the complement version. That is the reason first I have implemented the NOT gate, okay, and then I have discussed the 2-input NAND gate. Once if you have implemented 2-input NAND gate, after that this output if you are passing through CMOS inverter, then you will get 2-input AND gate. That's why here I am discussing the combination of basic gates and universal gates together. Okay, so just for easy understanding, okay, so initially I have started with inverter, then 2-input NAND gate, and with the help of those two we are getting 2-input AND gate. Now with this understanding, all of you give a try for 2-input NOR gate. All of you give a try. Next one, 2-input NOR gate. Here output you will get A plus B whole bar. Now tell me, see, regarding anyway you are having complement version, so regarding that there is no issue. Here you are having 2 variables A and B, that means we require 2 NMOS transistors. Now tell me, how we have to connect those two NMOS transistors? How we have to connect those two NMOS transistors? Yes, just observe here, you are having logical OR operator. Whenever you are having logical OR operator, that means parallel connection. Logical OR, parallel connection. Parallel connection, that's all. Okay. So just consider two NMOS transistors and connect them in parallel. Here AB are the inputs. So here the respective drain terminals and respective source terminals we have tied together. Okay, so that means parallel connection. Okay, right. Now tell me, now we have connected two NMOS transistors in parallel. So obviously we require two PMOS transistors. Since we have connected two NMOS transistors in parallel, now tell me how we will connect PMOS. We will connect PMOS in series, that's all. We will connect two PMOS transistors in series. So between VDD and output, we will connect the PMOS transistors. Between output and ground, we will connect NMOS transistors. If NMOS transistors are in parallel, the corresponding PMOS in series. If NMOS is in series, the corresponding PMOS will be parallel, like that, vice versa. Okay, exactly opposite we have to connect. That is the reason always draw the circuit diagram between the output and ground with the help of NMOS transistors. Once if you are able to draw the circuit diagram here, you can easily draw the circuit diagram for PMOS logic. That's all. Okay, so just make the tabular form. Zero 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 1 1 0 1 1. Now tell me, output will be connected to VDD. What is the condition? In which combinations output will be connected to VDD? See, you are having the path like this. If you want to connect output to VDD, then these two transistors, these two PMOS transistors, if they are on, then only output will be connected to VDD. Output will be connected to VDD if both the PMOS transistors are on. Okay, when the PMOS transistor will be on, if you are giving input as 0, so that means since we are saying that both the PMOS transistors have to be on, so that means both the inputs should be 0. Okay, so when both the inputs are 0, that time you are getting output as 1. Output you are getting 1. Okay, so in this case, both PMOS transistors are on. In this case, both PMOS transistors are on. Okay, now tell me, output will be connected to ground. In which combinations output will be connected to ground? All of you just think and tell me. In which combinations output will be connected to ground? See here, the moment if this NMOS transistor is on, then output will be connected to ground, because here drain and source terminals will be shorted. Okay, or if this NMOS transistor is on, then also output will be connected to ground. Or if both the NMOS transistors are on, then also output will be connected to ground. That means you are getting three combinations. You are getting three combinations. Okay. So here NMOS transistor will be on if you are giving 5 volt or logic high at the input. Okay. Then only NMOS transistor will be on. So here you can observe the moment if A value is 1, the moment if A value is 1, irrespective of B input, output will be connected to ground. Or the moment if B value is 1, irrespective of A input, output will be connected to ground. Okay. So total you are getting three combinations. Yes or no? Only A is 1, or only B is 1, or both A and B are equal to 1. Right? In all these three combinations, output will be connected to ground. Ground means 0. Okay. So in these two combinations, only one NMOS transistor is on. In these two combinations, only one NMOS transistor is on. Whereas in the last combination, both the NMOS transistors are on. Both NMOS transistors are on. Right. So now just observe this particular truth table, whether it is matching to the NOR gate truth table or not. Just observe, if you are considering OR gate, if both the inputs are 0 or if all the inputs are equal 0, that time you will get 0. Okay. For remaining all the combination you will get 1. So just the complement of that. That means here when all the inputs are equal 0, that time we are getting output as 1. For remaining all the combinations we are getting 0. Yes, we are getting the output as the complement of OR gate, that is nothing but NOR gate. Yes. So this particular circuit diagram is producing an output which is NOR gate of output, right? So that's why this particular circuit diagram is nothing but 2 input NOR gate with the help of CMOS logic. Okay. So if you are having the expression, from there also you can tell how many NMOS PMOS transistor pairs required. Just observe here, by default you are having complement version. Okay. So regarding that there is no issue because we are using CMOS logic. Okay. Right. Under the complement you are having two input variables. That means we require 2 NMOS transistors. The moment if you are using 2 NMOS, the corresponding PMOS also we require. Right. So that means together, okay, NMOS PMOS together we will call it as pair. We require 2 NMOS PMOS transistor pairs. We require 2 NMOS PMOS transistor pairs. Okay, right. Suppose if you are having a circuit diagram like this, how to write the output expression? Okay. So when you have observed that NMOS transistors we have connected between output and ground, and PMOS transistors we have connected between the VDD and output. Okay. So first of all, write the output expression in the complement version. Generally students used to forget to put the complement. That's why I am repeating. First put the complement in the first step itself. Okay. Now just observe the circuit diagram between the output and ground. Here you are having 2 NMOS transistors and both are connected in parallel. Parallel means among the input variables we have to perform the logical OR. That's all. Okay. So previously we have discussed regarding 2 input NAND gate. So there also we require 2 NMOS PMOS transistor pairs. There we have connected 2 NMOS transistors in series. Okay. Whereas here regarding the 2 input NOR gate, here also we require 2 NMOS PMOS transistor pairs, but here we have connected the 2 NMOS transistors in parallel. Okay, right. So with this understanding, I hope all of you can implement easily regarding 2 input OR gate. So here OR gate output is A plus B. Okay, but in the CMOS logic, by default we will get complement version. So what you can do, you can perform 2 times complement. Okay, so initially you will get A plus B whole bar with the help of this circuit diagram. Okay, after that this output you can pass through the CMOS inverter. So just draw the circuit diagram. So for the timing, just draw the block diagram only. Okay. Right. So we have discussed the two input NOR gate. So whatever the circuit diagram we have discussed, just I am representing as a single block. Two input NOR gate using CMOS. Here we are having two inputs A and B, and here the output you will get A plus B whole bar. A plus B whole bar. And this output we are passing through CMOS inverter. CMOS inverter. So here output you will get complement version of this one. So that means A plus B whole bar you are having at the input side. So now you will get one more complement. So both the complements will get cancel each other. So that means you will get normal function A plus B. A plus B. So here we require two NMOS PMOS transistor pairs. Here we require one NMOS PMOS transistor pair. So together we require three NMOS PMOS transistor pairs. Three NMOS PMOS transistor pairs. Okay. So in this particular session, we have discussed regarding the logic family introduction, what are the earlier logic families that we are having. Okay. And now currently in the GATE syllabus, they have restricted regarding the logic family to the CMOS logic family. Okay. Because I have already highlighted, with the help of CMOS logic, we are focusing low power consumption or low power dissipation. Okay. So that is the main reason why we are using nowadays, whatever the electronic circuits that we are using nowadays, all those circuits we are implementing with the help of CMOS logic, right? So whatever the logic gates that we have discussed in the third chapter, all those gates, okay, are all the logic functions that you can implement with the help of CMOS logic. Okay, here in this particular logic, between the VDD and the output, we are connecting the PMOS transistors. Between the output and ground, we are keeping the NMOS transistors. What is the number of NMOS transistors required? That many PMOS transistors we will use. Okay, throughout the operation of the circuit. See here, total we are having 4 input combination. For each and every combination, see together we are having 4 transistors. Okay, in each and every operation, only half of the total number of transistors will be on. Say for example, in the first case, both PMOS are on. That means here both NMOS will be off, like that. Okay, so that means total count wise, out of 4 transistors, only 2 transistors are on. That means if you are having 100 transistors, okay, 50 PMOS transistors, 50 NMOS transistors, out of 100 transistors, throughout the operation, only half of the total number of transistors will be on. And in fact, in general, we will change the inputs based upon the requirement, or in general, these inputs will come from the output of some other circuit. So even because of all these considerations, if you consider, during entire operation of the given circuit, no single transistor will be permanently on. That is the beauty of the CMOS logic. Whereas in the beginning of the other logic families, in this beginning of the session I have mentioned regarding the other logic families, okay, we are using one resistor permanently. Because of that, throughout the operation you are having static power dissipation, whereas in the CMOS logic, the power dissipation we are able to reduce. Okay, that is the beauty, because once if you are able to reduce the power dissipation or the amount of power that is required, while even though you are using most of the components that present in the given circuit, because of that you can utilize with the help of less power when you are able to operate the circuit. That means you are increasing the lifetime, right? Okay, so this is the main reason why we are focusing the CMOS logic. So in this particular session, we have discussed with the help of CMOS logic how we can implement the basic gates. So we have discussed the NOT gate, AND gate, OR gate, and then we have discussed the universal gates also, NAND gate, NOR gate, right? So with this understanding, all of you give a try how we can implement with the help of CMOS logic regarding XOR gate, XNOR gate. Okay, since this particular session is regarding foundation course, so in this particular session we have discussed the basic concepts regarding the CMOS logic, and with that understanding we have implemented the basic gates and universal gates also. Okay, so together in this particular, in our IMS GATE Academy YouTube channel regarding digital circuit subject gate foundation course, total we are having 16 sessions. So this is the 16th session and last session regarding the gate foundation course. So all of you kindly share, okay, this playlist. See, when you go to our IMS GATE Academy YouTube channel, so you just click on the playlist and there you can see the regarding digital circuits gate foundation course. So in that particular playlist you will be having 16 lectures regarding the digital circuit subject. So here in the initially we have covered regarding the first 3 chapters, number systems and codes, and then Boolean algebra and KMFs, and then logic gates. Okay, together regarding those 3 chapters, together 14 sessions we have discussed in the online live, right? And then in the last class we have discussed the basic concepts that are required for understanding the data converters, and in this particular session we have discussed the basic concepts of the CMOS logic, right? So all these sessions are very much helpful for the EC branch and instrumentation branch, whereas first 14 sessions are very much helpful for the CS branch, and 15 sessions are very much helpful for even electrical branch. Okay, right. So this subject is very important subject and scoring subject as for GATE exam point of view, and it is common for all the 4 branches, EC, electrical, instrumentation, computer science. So kindly share this video link with all of your friends and get maximum benefit from these particular sessions. Okay, those who couldn't attended these sessions due to any reason in the live, no issue at all. So all of you are having the opportunity to watch these recorded lectures which are available in our YouTube channel in your free time. So kindly share these playlist with as many students, as many friends as possible. Okay, and the students, okay, so from these lectures all of you will get regarding the digital circuit subject the basics. You will get thorough understanding regarding the basic concepts, and in fact we have discussed various gate questions also, and those questions we have solved based on the possibility both the conventional approach and then shortcut approaches also. All these methods are very much helpful for all of you, okay, in order to just be strong on the basic concepts of the digital circuits. Okay, if you are more interested to do the gate preparation seriously, you can enroll for our gate courses. Whatever the numbers that are scrolling on the screen, okay, you can contact them and you can enroll for our courses. Okay, so thank you everyone.